Hi folks, we're going to talk about the indefinite integral a little bit more and the net change theorem specifically. This is just a short theorem that goes into an area of integration that has a wide variety of applications, specifically, well, maybe I shouldn't say specifically, but certainly in physics and other sciences. So the idea of the indefinite integral, we've kind of seen a lot of this already. But we're using this notation of the integration symbol with some function where little f represents essentially a derivative of big F, which we would call big F the antiderivative of little f. So big F is an antiderivative, and that means that big F prime must equal f, little f. Okay, so a little bit of a reminder on the notation that we're using. So before we get started, let me point out that we've got a lot of integrals that we can figure out under our belts now. I'll start you off on this list. If you want to print this list out, it's on the slides posted on Canvas. But in any case, it would be a good idea to really memorize these before going into Calc 2, and I'd say even before taking the final exam in our class. But certainly before you go into Calc 2, you want to have a good intuitive sense of what all these indefinite integrals or antiderivatives are. So from this first one, we know that we can just simply pull that constant out. So where c is a constant. So just keep that in mind. Then something like this, we could kind of do the same thing, but we can go a little further. So where k is a constant, in this case, I pulled it out of the integral, so we just have the integral of dx. But of course, the integral of dx, that is just going to be x. And with all these, don't forget, we're looking for the most common antiderivative, which is kx plus some constant. So any antiderivative, did I say most common? I mean most general antiderivative. So we're looking for the antiderivative and then just tack a plus c, meaning we don't know what the original constant that we were adding is, because once we take the derivative of it, we would essentially get rid of that constant being added to the end. Now let me do one more before we move on, and I'll let you handle the rest of these. But like I said, it is a good idea to memorize each of these and understand it from an intuitive aspect. So here, with x to the n, this is just the power rule. So we add 1 to that power, and then divide by the new power. And again, do the plus c. All right, so let me stop at this point really quick before we go further and just point out this indefinite integral that we're talking about now, as opposed to the definite integral. The indefinite integral, it doesn't specify bounds here. So it doesn't say from a to b or anything like that. It's the indefinite integral, and whenever you see that, that just simply means that we should end up with a function. Whereas if we were doing the definite integral from, let me say, 0 to 2 of x squared dx, now you're going to actually end up with a number, which in this case I think is going to be 8/3. So you end up with a number as opposed to a function. So indefinite integral, you end up with a function. Definite integral, you end up with a number or a value. Now it is entirely possible, and you'll see this in Calc 2, that this could be not a number, but something more like infinity or negative infinity. But the idea is that it's not a function. Okay. Now let's look at an evaluation example here. So we want to evaluate this indefinite integral. So in other words, I need to find an antiderivative that has this as its derivative. Now, one way to do this is something called the substitution method, which we'll see in the next video. But in this case, I'm going to break this up in a special way into 1 over sine of theta times cosine of theta over sine of theta d theta. Now, one thing to notice is that 1 over sine, another way to write that is cosecant theta. And cosine over sine, well, that is just cotangent theta. And we have an antiderivative for cosecant cotangent, specifically negative cosecant theta plus c. So here would be my answer, negative cosecant theta plus c. And double check that by taking the derivative of cosecant theta and making sure you get cosecant theta cotangent theta. Of course, you get the negative, so that's why we have the negative on the front of our antiderivative. Okay, what about something like this? This is kind of like a rational function, except we do have a square root x here. But we could treat it with the same rules. Let me simplify this little piece here first of all. So I'm just going to call that x to the second power times x to the 1/2 will be x to the 2.5 powers, or maybe better, let's use an improper fraction and call that x to the 5/2 minus 3 over x, and then we have a dx off the end of that fraction. So now what I'd probably do is split this up. Oh, and I'm missing my x to the 3rd. So now what I'd probably do is split each of those numerator components up over this denominator and give them each an integral. So step by step, I would say this is 4x to the 3rd over x to the 3rd plus x to the 5/2 over x to the 3rd plus, and maybe I should call that minus 3 over x to the 3rd dx. And now I'm going to do two things here. I'm going to simplify each of these fractions, and I'm going to bring that integral into each term. All right, but keep in mind, just for notation purposes, as far as we're concerned at this point, I also have to bring the dx in. That's our differential. So this is going to be integral of 4 dx plus the integral of, well, now I have x to the negative, let's see, 3 x to the 3rd would be 6/2, so that's going to be negative 1/2 dx minus integral of 3 x to the negative 3rd dx. So now if I'm integrating each of these separately, the first one's easy enough. That'll be 4x. Now keep in mind, I do have a plus c. I'll call it plus c1. We actually don't need to do that. I'll explain why. This next one, and see if you follow me here, this will be 2x to the, let me get my page back, x to the positive 1/2. So I added 1 to this negative 1/2 power, and then I divided by 1/2, which is the same as multiplying by 2. All right, and then add your c2 here, minus 3, add 1 to that power, so this is actually negative 2, divided by the new power, negative 2. So these negatives turn it into a positive, plus a c3. Now, commonly, we don't actually write the c1, c2, and c3 separately, because notice, if we're adding all those constants together, we're just going to get one constant. So if I were doing this problem on my own without you watching me, I would come up with 4x plus 2x to the 1/2 plus 3/2 x to the negative 2, and then I would write a plus c at the end, which just combines the c1, c2, and c3 in one fell swoop. So, in other words, my answer would be 4x plus 2x to the 1/2 plus 3/2 x to the negative 2, and then plus c. Okay, so this brings us to the net change theorem. So the idea is that if we have this function, big F of x, and we know that f prime of x gives us the rate of change. So more specifically, y is a function of x, f prime of x gives us the rate of change of y with respect to, so abbreviated WRT, with respect to x. So with respect to how x changes. So we're getting the rate that y changes with respect to x changing. We also know that fb minus fa is the net change in y when x changes from a to b. So this is the y value at the endpoint, f of a is the y value at the start, and so if we subtract those, that's the net change of y when x changes from a to b. So combining those two ideas together, the integral of your rate of change gives you your net change, f of b minus f of a. So more specifically, the integral of your rate of change function from a to b gives you your net change. So let's look at a quick example, and then I'll move into a more specific example. If an object moves along a straight line with position st, its velocity, we know, is s prime of t. So then, its net change in position is given by integrating its velocity over a specified time period from time 1 to time 2. So we integrate the velocity function, and that gives us the net change from the first position to the second position, or the final position. So in other words, we've got a particle that moves from A to B, and where it is based on time depends on time 1 and time 2. So here's where it starts at time 1, and then here's where it starts at time 2. And we're not saying that it goes in a nice linear path. It might do something interesting like this, depending on what the velocity function is. Here, going backwards, it has a negative function. Going forwards, it has a positive value. Then it might go back again. But it's just moving in a straight line back and forth based on some function. Okay, to drive that home, let me do a more concrete example. Here we have a velocity function for some particle in meters per second is given by t squared minus 2t minus 8. Now again, it's moving along a straight line. So we want to do two things. I want to find the displacement, and I want to find the distance traveled by the particle. Now at first glance, that might sound like the same question, but I'll explain why that's not the case. Sometimes it is, they're the same, but sometimes they're not. So let me, first of all, find an antiderivative for this. So to find the displacement, we're going from 0 to 5 of v t dt. This is to answer question A, the displacement. All right, well, an antiderivative should be easy enough. We are going to evaluate t to the third over 3 minus t squared minus 8t. Now, I would plus a constant, but remember, if we're doing a definite integral here, we don't necessarily need the constant because it's just going to subtract itself out. So we can just pick any old antiderivative for a definite integral. In this case, I'm going to use the constant plus 0. And I'm going to evaluate that from 0 to 5. So first things first, I'm going to plug 5 in to my function. And now I'm going to subtract off what happens when I plug 0 in. But of course, that's going to be 0 minus 0 minus 0. So this comes out to be, well, let's do a little quick arithmetic, speed through this if you want. All right, so this is 125 minus 195, and I believe that comes out to be negative 70 thirds. Now, this might be confusing at first, because you would think if we're calculating the displacement, we should have moved somewhere. Why are we getting negative? Well, the idea comes from, let me take a look at the graph of our velocity function. So here's what our velocity function looks like on the interval 0 to 5. Now remember, when I calculated the definite integral, I calculated the area under the curve, but not exactly, right? Because some of the curve lies below the x-axis. So this area under the x-axis is actually counted as negative area in a sense. When I add these two areas together, I add the positive of the red area and then minus the area in the black here. And you can see the area in the black is bigger. So when you add those together, you're going to get a negative value. So what I actually want to do is not that. This is what I wanted to do for part A. But a lot of times what you want is the total distance. And so the total distance is the area or the distance they traveled the entire time. So I don't care that it went back and forth. In other words, if here is where my particle started, let me go back actually here. So for part B, I'm traveling along a straight line and I went here, but then maybe I came back and I went here and then maybe I stopped here. So part A, displacement, would just get you this little distance here, where they started compared to where they ended up. But the total distance, that is looking at the areas under the curve, the positive version of the curve, that's going to get you the entire distance that they traveled. And that should always be positive, possibly 0. Because your function is not going to go below the x-axis in this case. So in other words, you might be looking at the integral of the absolute value of your function. But to do that, what we need to do is figure out where is it below the x-axis. So let me figure out where is v of t, our function, where is that 0? Well, let's just solve it for 0 and see what we come up with. Well, let's see. A little premature on that equals. There we go. Equals 0. Does this factor? Well, let's see. I've got a 4 and a 2 will give me 8. Looks good. So we've got t minus 2 and t minus 4. Not quite right, but if I put a plus there, now I get the original function. So that means t equals -2 or 4. But of course, -2 is not in the interval that I'm interested in, that is 0 to 5. So I'm only concerned about 4. So now we got to figure out what happens when t is between 0 and 4. Well, let's see. If I plug in, I don't know, 1 into my function, it's pretty easy to see that the velocity function, or v, is going to be negative. So that means at 4, it must switch from being a negative function to a positive function. And now I can figure out that v of t, the integral of absolute value of v of t, is really 0 to 4 the negative of v of t, because from 0 to 4 our function is negative, so if we negate that, that's going to make it positive, and then integral from 4 to 5 of just the regular old vt function. Okay, now I already have my antiderivative that's going to work. So what I need to do now is, in this case, because the negative is just a constant multiplier, I can take that antiderivative and negate it. Alright, so then minus 2 t squared over, well, I'll put it over 1 just because I made a mistake here. That's not over anything. T squared and then minus 8t. And we're going to evaluate that from 0 to 4. And then plus the same antiderivative but this time evaluated from 4 to 5. Alright, well now I already know what happens when I plug 0 in. So now let me plug in 4. So this is going to be 4 to the third over 3 minus 16 minus 32. And can I go ahead and call this 64? But don't forget, I'm actually distributing the negative in, which is going to make this one positive and this one positive. And then I would subtract what happens when I plug 0 in. But of course, that is 0. Okay, now this plus comes down here to this plus. And I'm going to plug 5 in, which we know is 125 thirds, minus 25 minus 40. And of course, we already know that gets us this up here. All right, but then I'm going to subtract off what happens when I plug 4 in. 64 thirds plus 16 plus 32. So notice that's exactly this piece here. So you could double that if you want, however you want to attack this, but just arithmetic from here on out. So feel free to fast forward through the rest of this while I figure it out. In fact, maybe I'll fast forward the video for you. All right, so that's negative 128 over 3 plus 48, which is 96. So I've just doubled that. Then plus 125 over 3 minus 25. Maybe can I just call this minus 65? And then these two are going to combine to be negative 3 thirds plus 96 minus 65 is going to be plus 31. So this comes out to be 30. Okay, that's all I have for this section. Pretty quick section, but stay tuned for the next one. We're going to talk about the substitution method, which is essentially your first integration technique. You're going to start off Calc 2, most likely going over substitution again, and likely going over several other integration techniques. So this is kind of an introduction to the ways we integrate, which is generally considered much more challenging than finding the derivative. So stay tuned for that, and I will see you online.